In this video of optimization using MATLAB series, we will be talking about what is optimization. Optimization is a process of finding a point that minimizes a function. So there can be local minimas and global minimas in a function. A local minimum of a function is a point where the function value is smaller than or equal to a value at nearby points, but possibly greater than at a distant point. A global minimum is a point where the function value is smaller than or equal to a value at all the other feasible points. Optimization techniques are used to find a set of design parameters that can in some way be defined as optimal. In simple case, this process might be a minimization or maximization of some system characteristics that depends on X. In more advanced formulation, the objective function fx to be minimized or maximized might be subject to some constraint in one or more of these forms. There could be some equality constraints, some inequality constraints, and some parameter bounds like the upper bound and lower bound in the design parameters. Some of the optimization problem could be like maximizing the fuel efficiency of an engine, minimizing the risk in finance area, and maximizing profits. Let's take an example of engine efficiency. The plot shows how volumetric efficiency vary with respect to pressure ratio and revolution per minute. Our task is to find an optimal point where the volumetric efficiency is maximum. A simple manual approach to solve this problem could be trial and error method. For solving any optimization problem, first we need to take an initial guess. In this case, we will be taking the value of RPM as 3500 and pressure ratio as 0.5. The efficiency we will be getting for these value of pressure ratio and RPM will be 0.8963. Now we'll try to move in some direction and we'll try to find some other optimal point and the efficiency at that point. We change our pressure ratio from 0.5 to 0.6. For this case, we got the volumetric efficiency as 0.9146. We can see our volumetric efficiency is increasing in this direction. We will move one more step in the same direction and try to find the values at that point. If we change our pressure ratio from 0.6 to 0.7, our volumetric efficiency will be 0.9293, which is better than the previous point. And again, we'll repeat the same process and move in the same direction. If we change our pressure ratio from 0.7 to 0.8, we see that our volumetric efficiency comes as 0.8872, which is worse than the previous one. We'll move in the backward direction and try to find the efficiency at a point that is between the current point and the previous point. We'll take the pressure ratio as 0.75. For this case, we will see our efficiency is 0.9374, which is the best of all these observations. Now we will try to change the RPM. We will reduce the value of RPM from 3500 to 3000. Here we are getting the efficiency as 0.8622. So we are moving in a wrong direction. Now we'll try to search the value in the opposite direction. When we change our RPM from 3000 to 4000, our efficiency comes as 0.9126, which is not again the best value till now. Now at this point, we are somehow stuck in finding the optimal point. If we try to find the optimal point by this approach, it will take a lot of time, or maybe we will never reach to the solution. The drawback behind this approach is that we are kind of blind when we are searching the point. We do not know in which direction do we have to search the point. Here the optimization approaches becomes very essential. The optimization technique uses some approach to understand in which direction to search for the optimal point. In this way, the optimization techniques can guarantee you that that will be the optimal point and it will search for the optimal point in very less time. Now let's understand the optimization workflow. An optimization problem starts with a system or the objective function and some initial design variables or some initial guesses. We give these initial design variables to our system and then we check whether our objective is met or not. If the objective is not met, we modify the design variables and give it again to the system. We repeat this process until the objective is not met. Once the objective is met, we get the optimal design. All the MATLAB optimization techniques we are going to discuss in this series will be using the same workflow. Thank you for watching. I'll see you in the next video.